Okay, so hello everyone. Good morning. First of all, my name is Devansh and I will be your faculty for FAM. So, first thing first, we have already discussed what is the paper pattern for FAM, and by this time you must already know that there are two separate subjects under one roof, which is FAMS and FAML. For now, we will be starting off with FAML, and the first chapter for the FAML is survival distributions. So, as an actuary, the one of the major areas, one of the major chunk of areas where we work in is insurance sector. Okay, and in insurance sector you can work in either life insurance or you can work in a general insurance, irrespective of whether wherever you are working in. One thing which is very important for you to consider is when is the life or when is the machine which you have insured going to die or is going to get into an accident. Okay, so there are certain notations, there are certain things which you will have to learn before you can apply those stuff, right? So the data and all that, the probabilities and all that, the values and all that obviously will be supplied by the company which you are working in, and obviously you will also learn in future other papers, in other actuarial papers, on how to obtain those data, how to work on those data, how to correct those data and all that, so on and so forth. But for now we are going to learn how to use that data, how to use that data, how to figure out when is a particular life. Let's say we are just dealing with a life insurance policy, and as of now I just want to know when is a particular policy holder going to die. Let's say I am a term insurance seller. I have just insured multiple lives to whom I have just sold a term insurance policy. What is a term insurance policy? Term insurance policy is wherein I have just sold a policy to a particular life that says that if you die within this particular term, which may be let's say 40 years or 30 years, and if you die within this term, then we'll provide you with a certain sum of money as and when you die or at the end of year of your death. There can be different permutation combinations. Now it is possible that you might be paid in right at the time when you're dying, or it is possible that you are paid at the end of year of your death. Like for example, let's say if someone dies in June, it is possible that they are paid right at the end of the month of June or right at the time when they are dead, and it is also possible that they are paid at the end of year of that particular year. So for an insurance company, whenever they are pricing a particular product or whenever they are reserving a particular product, it is important for them to model when is a person going to die for a term insurance policy. So it is important for them to model when a person is going to die, right? So whenever a person is purchasing a policy, let's say they would be of 20-year-old. Let's say they are a 20-year-old person. Now we want to know when is that person going to live, or rather when is that person going to die, right? So if he is 20, we want to know how many more years is this particular person going to live before he dies, right? Now I can be interested in when is the exact point when he is going to die. If he is going to die in June when he is 60, I want to know that exact time when he is going to die. So this will be T20. You have already dealt in P, you have already dealt in FM that there are different random variables, right? Now you will apply those concepts in FAM. The lifetime random variable, the complete future lifetime random variable is T20. When a person is going to die, how many more years is he going to live is a random variable, because it is possible this person might live for 20 more years. It is possible that he might live for 10 more years or 9 more years or something to that sort. It is also possible that he might live for 100 more years. We don't know about that. So let's say if you are interested in how many more exact period is he going to live for, then we are interested in T20. We call this as complete future lifetime random variable. Complete future lifetime random variable. Complete future lifetime random variable. Now let us say we are not interested. Let's say this would have been the case. I would have been interested in complete future lifetime random variable of that particular person if I were making payment in as and when he was dying. If he dies in June, we will make payment in June. But if the case is let's say that irrespective of whenever he dies during the year, we are going to make the payment at the end of the year at the time of December when everyone is cozy. So let's say we are only interested in the year in which he is going to die, or rather how many more complete years is he going to live. We are not interested in his complete future lifetime. We are not interested in the number of months he is going to live. हम लोग को exact date, we are not interested in the number of days and number of months and all that. We are interested in the number of complete years he is going to live. Like whenever you go to a government agency, if it is possible that you are 20.54 something years, but obviously you won't say that we are 20.54. You will say that I am 20-year-old, right? So what you are essentially doing here is you are interested in curtate future lifetime random variable, which is nothing but Bot's function of T20. And what is Bot's function? It essentially means that, let's say if a person, this particular person, this 20-year-old is going to live for 20.54 more years, then I would put 20.54 more years, and this will be lower rounded off. This will be lower rounded off to 20 years. Now this would have been 20.99999, but it does not matter. It doesn't matter. It will still be rounded off to 20 years. It is possible that you, let's say your birthday is on 7 July, but if someone is asking your age on 6 July, you will say them that yeah, I am 20-year-old, right? So that is how this works. There are two different variables which models a lifetime random variable, or how many more years you are going to live for, and that is either T20 or K20. Both of them are first of all a random variable, and it is a future lifetime random variable of a person who is aged 20. Okay, and the next thing is you will have to deal with different notations under this variable. Like for example, in PFM you have already dealt with PDF and CDF and all that. So whenever we are interested in, let's say, what is the probability T0 is less than T. So herein, first of all, this is the complete future lifetime random variable of a person who is aged 0, basically a newborn baby. Okay, and we are interested in the probability of knowing whether that person will live for less than T years or not. 0 years, right? So this will be written as TQ0. This is the actuarial notations which we will use very extensively in the FAM examination, especially in the FAML part. So it essentially means that we are asking for what is the probability that a person who is aged 0 years will live for less than T years. He will live for less than T years, and this is TQ0, and we also have probability T0 is greater than T, which essentially means 1 minus probability T0 is less than T. You are big enough to know how we are deriving this relationship, but there is a separate notation for this, which is TP0, which essentially means the probability of measuring whether a life-born baby would live for at least T more years. Whether he would live for at least T more years. Now it is possible that you are working in a pension company. If you are working in a pension company, your client might be working as of now, he is already making contributions to his pension fund, but he will get the pension payment as and when he retires. So there is a gap between the time he is making a contribution and when he will receive the payment. So you are interested in knowing whether the person would survive till that period. Should we make a reserve for that? Should we keep that money aside? Should we keep that money aside in a reserve, or should we just spend it and party and all that? But for that you will have to know whether that person will survive till that period. So for that you will need probability T0 is greater than T, which is TP0. Now you have a third notation as well, which is nothing but a combination of these two notation, which is T deferred U Q0. This is nothing but an extension of these two notations. Now this notation is definitely looking very overwhelming for me. The first time I saw it, I was very overwhelmed by it, and to be honest, it is something which you should be overwhelmed by it. But it can be made very easy. What this notation essentially means, that first of all my person is still 0 year old. That thing is for sure. Next is this sign T, this slash thing. This is known as T deferred. It essentially means that I have deferred the probability for T years, which essentially means that I am not interested in whether this person will die now or not. I am interested in whether this person will die within U years, but T years from now. So essentially I am saying that this person can live for T more years, but after that he will have to die within the next U years. So let's say if I am concerned with 10 deferred 5 Q0, it essentially means I am saying to the newborn baby that you can live for the 10 years. You can live for the first 10 years, I don't have any problem with that. But there is a high probability, I am measuring the probability that you will die within the next 5 years, which is basically saying I am measuring the probability that he will die between 10 and 15. That is what it essentially means. And now coming back to the general notations, it essentially means that the person will survive for T years and then he will die within the next years. That is what we have done here. Okay, so this was a very simple notation. This was a very simple introduction of the first chapter, which is survival distribution. This chapter has not yet ended. There are other things which you will have to learn within this chapter, but this was a short recap. I hope you liked it. Thank you.